Conrad will be speaking about Chebotarev.
All right, thank you very much. So I want to begin by today giving some background to explain where the Chebotarev density theorem kind of came from. So I hope by the end of the lecture I'll be able to state the result, and then we'll have enough preliminary information to kind of appreciate roughly what it's saying. So I should say at the beginning that this course is going to at some point start assuming some familiarity with some aspects of algebraic number theory and Galois theory. I'll give some examples of things in some simple cases, quadratic fields and cyclotomic fields. So we're going to begin by not stating the Chebotarev density theorem. It's a somewhat technical statement if you haven't seen it before, but we're going to start with something that came quite a bit earlier, and that's Dirichlet's theorem. So I suppose you could say Dirichlet's theorem is kind of like Gauss's theorem or Euler's theorem. Which one is that? Well, Dirichlet worked in different areas of mathematics, number theory, analysis. So Dirichlet's theorem, I mean here, is theorem on primes in arithmetic progression. And so that's the statement that if you have relatively prime numbers, A and M, then there are infinitely many primes that are congruent to A mod M. And we can even count these primes, estimate how many there are. And we can do it in a way that feels like a very natural method of counting. If you count the number of primes up to x that are congruent to A mod M, and you divide by the count of the number of primes up to x in total, that this proportion is somehow independent of the A. So there are phi of M choices for A that are relatively prime to M, and this proportion is the same value for all the values of A, 1 over phi of M. So if we take the limit for large x, and this limit is 1 over phi of M. All right, so let's just recall phi of M is the total number of integers relatively prime to M from 1 to M. Okay, so there are an equal proportion of primes in every congruence class that's relatively prime to M. Now, I should say this is not the version of Dirichlet's theorem that Dirichlet himself was able to prove. He was not able to count primes congruent to A mod M in this particular way. This was only possible essentially like 50 years later, towards the end of, or 60 years later, towards the end of the 19th century, once people were able to prove the prime number theorem. So Dirichlet's own version of his theorem, he had some more complicated kind of wacky way of counting that had a limit of 1 over phi of M. But I'll state it in this way. It feels more intuitive. So as an example, if we took M equal 10, say A equals 3, then if you want to count the primes that are 3 mod 10, which is the primes with the units digit 3, then the number of these primes as a fraction of all primes up to some bound, this limit is 1 over 4, right? Phi of 10 is the number of integers relatively prime to 10. And so there are 4 of them. So, for example, if I took some values of x, I'll tell you what the ratio looks like at x. Let's go with the powers of 10. We're not going to start at 10. We'll start at 100. It's a little bit more interesting. And the ratio at every step is a rational number. At 1,000, by accident, it literally is 1/4. But in general, it tends to 1/4. Okay. So the proportion of primes in every congruence class relatively prime to M is the same. There are phi of M possibilities. I mean, how many primes are going to be congruent to 2 mod 6? It's not a very interesting condition, or 4 mod 6, or 3 mod 6. 1 mod 6 and 5 mod 6. Those are the more interesting options in this 50-50, 1/2 for each possibility. So this is Dirichlet's theorem. Some people would say it's kind of the first theorem in analytic number theory, using group theory, finite Fourier analysis, complex analysis, real analysis, depending on how you approach it. So this theorem, we would like to generalize it. How do you generalize a theorem like this? Talking about how often a prime can be congruent to A mod M. So here's one way you could generalize this. One possibility is to replace the condition that P is A mod M by saying P is, well, A plus Mn, for some n, it's the value, it's a prime value of a polynomial. You're saying, like, if the polynomial A plus Mx, and I'm saying at certain integers it takes on prime values. And so what you could do is you could try to count prime values of a polynomial. I don't know, some polynomial with integer coefficients. It could be a linear polynomial, it could be a quadratic polynomial, so maybe it could be a linear polynomial, or maybe it could be a quadratic polynomial. A famous example is like primes of the form n squared plus 1. Right? It's still unknown there are infinitely many primes of the form nt squared plus 1. So you could replace generalized Dirichlet's theorem by thinking of a congruence as saying a certain linear polynomial is a prime value, and then just talk about how often do we expect a polynomial should take prime values. So this goes in the direction of what would be called the Bateman-Horn conjecture, and that's not something that we're going to be talking about, but if you want to look up what can be said about prime values of polynomials, or at least what's conjectured about them, then there are statements where Dirichlet's theorem is a special case of a linear polynomial. You could have multiple polynomials, like twin primes, t and t plus 2. When are they both prime? But this is not what I want to discuss. I want to go in a different direction, present a different way to generalize Dirichlet's theorem. And the different direction uses Galois theory. What do I mean by that? We're going to reinterpret the statement of the theorem as not being about congruence classes, but being about Galois groups. So the key observation here is that we can, should I change the color? Let's try blue. Okay, so we can think about Dirichlet's theorem in terms of groups, and in particular, in terms of the group Z mod M star, the units mod M. Because, for example, phi of M is the size of that group, number of units mod M, and if I told you A is relatively prime to M, well, that will tell me that A mod M lives in this group. And the connection to Galois theory is that the Galois group of the mth cyclotomic field, Q adjoin a primitive mth root of unity, is isomorphic to this group. So we can interpret this group in Dirichlet's theorem as being a Galois group. So let me rephrase. Whoops. Can I move this? I think I can move this down a little bit. So we could rephrase Dirichlet's theorem. Dirichlet says that if you have an element of this group, then if you look at the primes up to x that reduce to that element and divide by all the primes up to x, that this limit is 1 over the size of the group. So we can think about this group of invertible numbers mod m as a Galois group. How does that work? How does that work? So the point is that, so Q adjoined a primitive mth root unity. This is a splitting field of to the m minus 1. There were m different mth roots of unity. And if I gave you one of order m, its powers give you everything else. And if I gave you an element in the Galois group, it's an automorphism of the field, Q zeta m. And what is it going to do to the mth roots of unity? Well, it has to go to another mth root of unity. It's a field automorphism. It has to go to another root of unity of exact order m. So it has to go to some power that's relatively prime to m. If I gave you an eighth root of unity, the odd powers have order 8. The even powers, it drops. So the automorphism of Q adjoins zeta 8 can only go to zeta 8 to the first, third, fifth, or seventh. And it turns out that all of these possibilities really do occur. Okay, this is something one sees in the course on Galois theory. Sending zeta m to any power that's relatively prime to m, and then propagating by sending formulas in zeta m to formulas in zeta m to the a. This will be a field automorphism, and they all occur for all of these options. And so you get everything that's possible. So what I would like to do now is find a way to replace, goal is to replace the role of the units mod m, thought of as a Galois group, in Dirichlet's theorem. I would like to replace it with a general Galois group of a Galois extension of Q. Doesn't even have to be an abelian Galois extension, okay? But it's not at all obvious what you're supposed to do with the concept of a prime number reduced mod m. I mean, if I gave you, for example, I don't know, let's say K is, I don't know, Q adjoin the fourth root of 2 and I. So this is one of the examples in a course on Galois theory where the Galois group is not abelian. The Galois group in this case, what is it? It's a degree 8 extension. Everything's determined by what happens to the fourth root of 2 and I. And so you have your two basic elements, or fourth root of 2 goes to I fourth root of 2, another fourth root of 2, and I is fixed. Or you have complex conjugation, fixing the fourth root of 2 and changing I to minus I. And these two elements generate the Galois group in a way that looks like the dihedral group of size 8, D4. Okay, where sigma is like the rotation R and tau is like the reflection S, their relations. And so what would it mean if I took a prime number, instead of saying, okay, I can talk about 3 mod 10, but like, what would it even mean to say, okay, I want to associate to 3, to the prime 3, I want to associate an element of this group? I mean, it's not all clear what that's supposed to even mean. Right? Previously in Dirichlet's theorem, I have the units mod 10, and I can take 3 and reduce it mod 10. But here it's like, how do I turn prime numbers into elements in this Galois group? It's totally non-obvious what you're supposed to do. So I want to explain how we're going to do that. So so this is kind of the key issue here. How do you turn prime numbers into elements in the Galois group that generalizes the much simpler idea of taking a prime number and just reducing it mod m? Okay, which doesn't sound like much is going on, but here it's sort of, yeah, what are we supposed to do? So here's the basic strategy is we're going to we're going to turn prime ideals in the ring of integers upstairs into elements of the Galois group. And then we're going to see how that varies for different primes that divide the same prime number, different p that divide the same prime number. So for example, if we take Q adjoin I over Q, the ring of integers is Z bracket I, and if you try to do factorization here, two factors is 1 plus I, 1 minus I in Z bracket I, but up to units, they're actually the same number up to a unit, and so it's really the square of 1 plus I. 3 stays prime, and in Z bracket I5 breaks up into 2 prime elements. And so here are decompositions, and what I want to do is somehow associate to, maybe I should have, associate to these primes, turn them into elements of the Galois group of Q adjoin I over Q. What is the Galois group of Q adjoin I over Q? It's the identity and complex conjugation, changing I to minus I. And so we want to turn the primes there into elements in the Galois group, and then see, for example, with 1 plus 2i and 1 minus 2i, if they go to the same thing, then we'll say, okay, 5 goes to that. If they go to different things, well, then we have to figure out what's going on. So we want to turn prime ideals in the ring of integers upstairs into elements in the Galois group, and then for different primes that divide the same prime number, all prime ideals arise as factors of the decomposition of a prime number down in the integers when thought of up in OK, and then see how this method in step 1 varies if I pick different prime ideals that divide the same prime number. So at this point, to explain how do you turn a prime ideal into an element of a Galois group? What does that mean? So this involves a discussion about the behavior of finite fields. You see, to every prime ideal, or to any ideal at all, I can turn it into a ring, namely the ring OK mod that ideal. Okay, so what I'll do is for every ideal in the ring of integers of a number field, I can create the ring OK mod A. And what I don't care about the 0 ideal, okay? Modding out by 0 isn't collapsing at all. And the thing about when you mod out by an ideal, you get a finite ring. Okay? Just like Z mod M is finite if M is not 0. The ring of integers, mod a non-zero ideal, is a finite ring. How big is that ring? What does it look like? So for example, if I asked you, like, how big is Z bracket I mod A plus BI? Or how big is Z bracket root 2 mod A plus B root 2, where A plus BI and A plus B root 2 are not 0? Then the size turns out to be connected to the norm, the usual notion of the norm of a quadratic element. So in fact, it turns out to be a squared plus b squared, or the absolute value of a squared minus 2b squared, things that we often call the norm. Yes, question? Yes. Yes. So if you actually draw correct fractal letters, and A is supposed to look like that, but that looks totally bizarre, so we're not going to do that. Yeah, it's sort of like, imagine you always wrote your A the way they look printed. That would be strange, but that's what we're doing. I mean, okay, maybe there's somebody out here who writes their A's like that. That's fine. Okay, yes. So I don't think we'll get to writing capital fractor P today, but that'll happen eventually. That'll be fun. So yeah, so it turns out it's totally unobvious that the size of a quadratic ring modulo an element is in fact the absolute value of the norm of the element in the sense of ring theory, multiplying the element by its conjugate in the quadratic setting. And so for that reason, we call the size of this ring, we call it the norm of the ideal. Right, the norm of A. It's the size of this ring. I'm not giving you a formula. I'm giving you a word, a name for it. How you would calculate it, well, depends on what the ideal is. If it's a principal ideal, it really is the absolute value of the ring theoretic norm of a generator. But if it's not a principal ideal, well, I mean, let's take a look at an example. How big? What's the size of this thing? So, for instance, if I gave you, let's take z bracket root minus 5, and let's take ideal. I'm going to write it as frac p because it'll turn out to be a prime ideal. Let's take the ideal 3 and root minus 5 minus 1. Okay, so it turns out that the ideal 3 breaks up into a product of two ideals that have generators that I can describe in this way. And how large is the ring z root minus 5 modulo these ideals? So z root minus 5, you could think of as z bracket x mod x squared plus 5. And so if I mod out by the first ideal, if you look at the way it appears, and you look at the way I'm going to rewrite this, then together, this basically is like z bracket x mod, well, how do I want to say this? Let me first write it out more explicitly. Sorry. Z root minus 5 modulo 3 root minus 5 minus 1. So when I mod out by this ideal, I'm forcing root minus 5 to look like 1. So everything's going to look like an integer. A plus b root minus 5 is going to turn into a plus b because root minus 5 turns into 1. But then, because I'm modding out by 3, integers should only matter mod 3. So there's a whole kind of two levels of collapsing here, so that at the end of the day, it turns out to basically look like z mod 3. It has size 3. The norm of this ideal is 3. When you mod out by p, you get a ring of size 3. It's a field, z mod 3. And in the same way, the other prime ideal also has norm 3. When you mod out by the second ideal, p prime, it looks like z mod 3 in a slightly different way, because then root minus 5 is identified with minus 1 instead of plus 1. So for small examples, you can work out what the ring mod the ideal looks like, and the size of that, well, that's going to be the norm of the ideal. So it's a measure of size for ideals. Now, in this particular case, the decomposition, we had two prime ideals with the same norm. It's not always going to happen like that. So, for example, if I take z bracket the cubed root of 2, which is the ring of integers of q adjoin cube root of 2. Remember, if it was z bracket the cube root of 10, that would not be the ring of integers, as we saw in my Wiefer prime lecture. But this is the ring of integers of q adjoin the cube root of 2. And in this setting, so you can think about it as z bracket x mod x cubed minus 2. And in this setting, the polynomial x cubed minus 2, if I factor it mod 5, it breaks up into a linear and quadratic polynomial. Those are the irreducible factors. And for that reason, you get a decomposition of the prime 5 in Z bracket the cube root of 2 to a product of two prime ideals corresponding to those two irreducible factors of x cubed minus 2 mod 5, where P is the ideal generated by 5 and the cube root of 2 minus 3, and P prime is the ideal generated by 5 and the cube root of 4 plus 3 cube root of 2 plus 4. I'm just plugging in the cube root of 2 for x in those formulas. And so these are the prime ideals in the factorization of 5 inside this ring Z bracket cube root of 2. And in relation to the way that x cubed minus 2 decomposes, when you mod out by the first ideal, you're going to get a ring of size 5. And when you mod out by the second ideal, you're going to get a ring of size 25. Okay, so essentially what's happening here is that when you mod out, when you mod out by the first prime ideal, because of the way the first prime ideal looks, it's basically going to look like, we have z cube root of 2 mod 5 cube root of 2 minus 3. And so when you mod out by that, you make cube root of 2 look like 3. So everything's going to look like an integer. You're also modding out by 5. And so all you're going to be left with at the end is z mod 5. It has size 5. While if you mod out by the second prime ideal, then, well, actually, that wasn't, that wasn't isomorphic, literally is equal. So the second, so the second ring is essentially going to look like z mod 5 bracket x in relation to the second factorization. And this is a field of size 25. Don't write z mod 25. It's not z mod 25. Z mod 25 is not a field. It's a field of size 25. And so what we see here is sometimes when you decompose a prime in a ring of integers into prime ideals, the different prime ideal factors might not be of the same size, so to speak. The norms might not all be equal. In the quadratic case, we saw that they both had norm 3 in that example. But in this example here, 5 breaks up into two prime ideals, but one has norm 5, the other has norm 25. Okay. So it turns out that when you're dealing with Galois extensions, the second kind of situation never happens. That the prime ideal factors will always have the same norm. We'll get to that eventually. So what we want to do now is take a prime ideal in a Galois extension in the ring of integers and turn it into the ring mod that ideal so we get a finite field. Okay, so now it's time to let's switch colors. Let's go to purple. Oh no, we had purple before. Oh no, this is a bit of different purple. Okay, so now let's we're going to turn prime ideals in a ring of integers when we're working with a Galois extension. We want to turn them into elements of the Galois group in a way that should generalize the idea of turning a prime number p into p mod m in the setting of Dirichlet's theorem. So how is this going to work? Well, we have a prime ideal. Take a prime ideal in the ring of integers, and we can get from it an algebraic object, the field, OK mod that prime ideal, finite field. Now, what is so special about a finite field? Well, the nice thing about a finite field is that they are always Galois extensions of some z mod p. So if I took, for instance, let's take this example up here. Well, I guess we're using a different color now. So special feature of finite fields is that, so the size is always a prime power. No such thing as a field of size 6. And if, let's write f sub p to the f is a field of that size, and for every prime power, there really is a field of that size. It contains the subfield Z mod P for that prime, and it's a Galois extension of that. And not only is it a Galois extension, but there's a very, very special element, an automorphism whose iterations give you all automorphisms. It's generated by the P power mapping. The P power mapping on a field of P power size and its iterations give you all the automorphisms of that finite field. So for example, let's take as a field of size 9, let's take Z mod 3 bracket X mod X squared plus 1. X squared plus 1 is irreducible mod 3. So when you mod out by that, you really do get a field. And because the remainders is just constants and linears, there's three choices for each coefficient. So it's just going to be a plus bx mod x squared plus 1, where a and b only matter mod 3. And so you get 9 possibilities. And so it turns out that this is a quadratic extension. It's a degree 2 extension, and the automorphisms are exactly the identity function and the third power function. Okay, there's 2 elements that are 2 automorphisms of F9 fixing F3, the identity and raising to the third power. Or if we took a field of size 27, for example, Z mod 3 bracket X mod X cubed minus X minus 1. So that has 3 coefficients, a plus bx plus cx squared. Then the automorphisms of that big field will automatically fix the bottom field. And the automorphisms are the identity, the third power function, and the 9th power function. If you iterate the third power twice. If you go a third time, the 27th power function is the same as the original identity, and up in the quadratic example, if you iterate the third power twice, the 9th power, you get back to the identity. So you can keep iterating, but eventually you're going to cycle back through. So the automorphisms are always iterations of the P power map. And what we can now do is take an element in the Galois group for a number field and try to turn it into an automorphism on the finite field, the ring mod that prime ideal. So now, if we go back to the setting of the Galois extension, and we take a prime ideal, and it divides some prime number, like 1 plus 2i divides 5 in Z bracket I, then what we can do is we can turn any element in the Galois group into an isomorphism. You take the ring mod that ideal, and I would like to apply the automorphism to the representative, but the catch is that if you're congruent mod an ideal and you apply an automorphism to the 2 elements, the difference will be congruent mod the automorphism applied to the ideal. meaning you hit the automorphism on everything in the ideal, you get a new ideal. It'll also be a prime ideal, but it might be different. And so we don't quite get the same thing back. So for example, in Z bracket I, if we 5 breaks up into 1 plus 2i, 1 minus 2i, 2 primes, then complex conjugation is an element in the Galois group of Q adjoin I over Q, and complex conjugation will turn Zi mod 1 plus 2i into Zi mod 1 minus 2i. If you complex conjugate congruent elements, you will get congruent complex conjugates, but the modulus is going to be conjugated as well. Yeah? So what I really want to do is look at the elements in the Galois group of K over Q that fix the prime ideal, in the sense that they bring it back to itself. So if we have a prime ideal and something in the Galois group preserves the prime ideal, if you hit it on everything, you get the whole thing back. Not that it fixes every element, but just the whole thing is itself. Then applying sigma gives an automorphism of OK mod P, right? If two things are congruent, then if you hit it with that, it'll still be congruent for the same modulus, okay? So, for example, if I took Z bracket I mod 3, 3 stays prime in Z bracket I, 3 doesn't break up. This is a field of size 9. Then I could take elements mod 3 and send them to their complex conjugates, because if I have 3 times a Gaussian integer and I complex conjugate it, it's still 3 times a Gaussian integer. So the modulus is still the same when I apply complex conjugation. So in this example, complex conjugation turns Zi mod 1 plus 2i into Zi mod 1 minus 2i. That's something different. But for the prime 3, it actually, everything stays put and it's a field. So what I would like to do then is think, if I have an element in the Galois group that fixes the prime ideal, that means that if I look at it on OK mod the prime ideal, it will look like some iteration of the Pth power map. So from the fact that I get an automorphism of this field, what that means then is, from our knowledge of automorphisms of finite fields, this has to look like some iteration of the Pth power map on everything. So for each element, so if we fix the prime ideal, preserve it rather, then if I apply it to the cosets in OK mod P, it'll be an automorphism of that field. And we know the automorphism of the finite field, when P divides the prime number of P, size is a power of P. It'll look like iterations of the Pth power map. Do we get everything in this way? For example, do we get the Pth power map in this way? And the answer is yes. There was always going to be something in the Galois group that looks like the Pth power map on a prime ideal that divides the prime P. So this is something that Frobenius had discovered. Dedekind had discovered it earlier, but he didn't publish, so he lost the fame on that one. But he did other things. So it turns out that for each prime ideal in the ring of integers where it's a Galois extension of Q if we say it divides some prime number. Every prime ideal arises with the factorization of a prime number. There is going to be an element in the Galois group that looks like the P power function on the ring mod that prime ideal. This is a mouthful. So what's an example of all this? So let's go back to in Q adjoin I, 3 stays prime in Z bracket I, and Z bracket I mod 3 is a field of size 9. In fact, if you think about it, this literally looks like Z mod 3 bracket X mod X squared plus 1, because Z bracket I is Z bracket X mod X squared plus 1. It's a model of a field of size 9 that I wrote down before. So, so the 3 generates a prime ideal in Z bracket I. Okay, what that means then is when you mod out by it, you get a field of size 9. Something has to look like something in the Galois group of Q adjoin I over Q. That's the identity and complex conjugation. One of those is going to have to look like raising to the 3rd power. Which one on Zi mod 3 looks like the 3rd power function? So I claim it's complex conjugation. Looks like the 3rd power map. Well, I claim that complex conjugation looks like the 3rd power function. Why is that? Well, you see, when you're working mod 3, raising the 3rd power at least is always additive. And because it's additive, a plus bi cubed is going to look like a cubed plus bi all cubed, mod 3. And for integers, raising to the 3rd power is not changing anything, right? From our little theorem, anything to the p minus 1 is 1 if it's not 0, so anything to the p is itself in the integers. And since I'm modding out by 3 integers, everything only matters with them, mod 3. So it looks like, I guess I'll write a cubed plus b cubed I cubed. But integers look like themselves, and I cubed is literally minus I. And isn't that what a plus bi conjugate is anyway? So we see that for the prime number 3 in Z bracket I, the prime ideal generated by 3 in Z bracket I, if you mod out by that, complex conjugation on that field looks like the 3rd power map. In fact, quite generally, if you gave me a prime number that's 3 mod 4, everything that I just discussed goes through. It generates a prime ideal in Z bracket I, and the complex conjugation looks like the 3rd power function, the P power map modulo that ideal. So the identity, definitely not the identity. The identity does not look like in this example here, the identity function is not the 3rd power map, because on a field of size 9, the 3rd power map only fixes 3 things. The identity fixes everything. So it can't be the identity, and it is complex conjugation. So this is a way of turning prime ideal into an element in the Galois group. Oops. So let's celebrate by changing to green. Okay, so So for a Galois extension and a prime ideal, non-zero prime ideal, we can associate to each, we can associate to P an automorphism sigma in the Galois group of the number field so that it looks like the P power map on the residue field on OK mod P. It looks like the P power map. So we saw in these examples that compass conjugation was the answer in this case. So immediate question is this even well defined? There could be multiple sigmas that look like the same thing. So it turns out that there's almost always only one choice. This automorphism is unique if the prime number P that this prime ideal divides is, well, from the language of algebraic number theory, if it's unramified, all that means is just that basically there are only finitely many ramified primes, and so this, except for those where there is genuine ambiguity, there is only one choice. Okay, so basically for all but a finite number of prime ideals, there really is exactly one element in the Galois group of K over Q that when you apply it to elements of OK mod that prime ideal, it looks like the Pth parent. There is one choice. And so this special element, this is called the Frobenius element. So we call this sigma the Frobenius element of the Galois group associated to the prime ideal. So again, what does it mean? It's the one element in the Galois group of the number field extension that when you look at it on OK mod that prime ideal looks like the little Pth power map. And okay, if the primes are ramified, then this is ambiguous, but that's only a finite number of things, so don't worry about it. It's kind of analogous to, like, in Dirichlet's theorem, you don't reduce a prime that divides M, right? We only look at the primes that don't divide M. So it's kind of like that. Literally, it exactly corresponds to that if you take K to be a cyclotomic field. So what happens if we start to, as an example, let's take the field Q adjoin I, and so the ring of integers is Z bracket I, then if I take a prime that's 1 mod 4, then it breaks up into a product of some element and its conjugate, like 5 is 1 plus 2i, 1 minus 2i. If I take a prime number that's 3 mod 4, it actually stays prime in Z bracket I. And so the so in the first case here, the Frobenius of pi and pi bar is the identity. And the second case, the Frobenius of this prime ideal is complex conjugation. All I'm saying here is that every number looks like its Pth power mod a prime in the first case because those prime elements have norm P. The residue field has size P, so the Pth power map really is looking like the identity. But in the second case, if P is 3 mod 4, then complex conjugation looks like the Pth power map. I showed you that when P was 3, and it works in the same way when P is 7 or 11 and so forth. So we have two different kinds of choices here. So last step before I state the Chebotarev density theorem is, what if we start with a prime number, not a prime ideal, and vary the prime ideal that divides it? How do the Frobenius elements change? What kind of how are they related to each other? How do the Frobenius elements at all these prime ideals vary? And the answer is, if you change the prime ideal dividing the same prime number, you will get a conjugate element. They might not literally be the same, but they're going to be conjugate to each other. It's kind of like in the theory of group actions, where at different points in the same orbit of a group action, you'll have like conjugate stabilizer subgroups. There's a lot of conjugation stuff going on in that kind of setting. So, is there a question? Yes. It could be like 1 plus 2i, 1 minus 2i if p is 5. Or if p is 13, it's 1 plus 3, 2 plus 3i, 2 minus 3i. Or if p is 17, it's 1 plus 4i, 1 minus 4i. Yes, it's always, when a prime number is 1 mod 4 in Z bracket, it always breaks up into two numbers that are conjugate to each other. Yep. And so they vary, they run through a conjugacy class. So it turns out that while you can associate to prime ideals upstairs and individual elements in the Galois group by this complicated process, if you try to think about it in terms of the prime number downstairs, you're kind of stuck with a conjugacy class instead of an individual element. Unless the Galois group is abelian, then all the different prime ideals over the same prime, their Frobenius elements are all the same thing. So we're now ready to state the Chebotarev density theorem. So the Chebotarev density theorem says that if in the original version proved by Chebotarev for Galois extensions of Q, if you have a Galois extension and you have, I'll call capital C, put a little hook on it, capital C is a conjugacy class in the Galois group, then if you look at the prime ideals with norm up to X, whose Frobenius at P is in that conjugacy class, I'm sorry. I guess I should, let me just stick to, no, take the prime numbers up to X, whose, where, such that the Frobenius elements at the prime ideals that divide P are in that conjugacy class, and divide by the set of number of all primes up to X, that as you go to infinity, this limit is the size of the conjugacy class over the size of the group. So you ignore the finite number of primes where this correspondence makes no sense or is ambiguous. So every conjugacy class in the Galois group occurs as the Frobenius elements of all the prime ideals over some prime number, and it does this proportion of the time. And when the field is a cyclotomic field, then the conjugate classes have size 1. The conjugacy classes in the Galois group are the units mod M, and this literally becomes Dirichlet's theorem. Okay, so next time I'll discuss some examples of computations of this, showing you what it looks like, and then I'll discuss how you go about proving such a statement, starting recalling Dirichlet's theorem, and then how you have to modify things to handle this Chebotarev case. And then after we discuss the proof in a sketch, then we'll talk about applications. What can you do with this kind of a result? So that's it for today.